Well, we can get started anyway. Welcome back. Thank you for coming, I guess. I don't, I don't know what's going on. But we can continue talking about the derivative, all right? That's what we started last time. The Brzozowski, this derivative. All right? This has to do with which languages are or are not regular languages, although we didn't really get to the connection yet. We were just talking about as an operation, it's something that you do to a language, and it gives you another language. So for some letter A, the derivative with respect to A of some language L, the definition is it's all strings X such that AX is in L. So what you do is you look for all the strings in your original language which started with A, and then you remove the A from them. And the result is some other set of strings, and that's called the derivative with respect to A. Or you can do this really for any string, or for any string, say Y, you can do derivative with respect to Y of L. And the definition is the same. You look in your language for all the words which start with that string as the beginning of it. And then the derivative is the set of the ends of those strings, having removed the Y from the beginning. All right? This is the derivative. Why is it called the derivative? Actually, I'm not 100% sure about this. There is something like the product rule, which works for the derivative, although I don't really want to get into it. Oh, somebody's mic is on. Sorry, I can't tell from you guys in the Zoom, but thank you for policing one another. Yeah, this is the derivative. Let's do. So I said at the very end last time some cute examples using the English language. So if I let E be the set of all English words, then for instance let's say dr of E. This includes strings like. The derivative with respect to R, it means you choose some string in the original set which begins with R, and then you take the R away, and you say what's left over. So anyone want to toss out something that will be in this set?
Ed.
What?
Ed.
Ed? Okay, yes. Ed. Why is that in dr of E? It's because red is a real word in E, since red is in E, right? Or something like, I don't know, recess, because recess is in E. All right, we only do it for the first letter, right? The derivative is not about removing letters in the middle of the word or on the end of the word or anything like that. It's just about the very beginning. All right. That's for a single letter, but like I said, you can do this for an entire string. So for instance, D by D of, I looked this up actually, D bop of E. Anyone think of a word or a string which is in this set? I actually looked at my list of English words, and I am prepared to show you a complete listing of all the strings in this set. Anyone think of one? You should try to think of a word which begins with BOP, and then tell me what the rest of it is, not including the BOP. Folks at home can shout it out too if you like. How about this? That's one thing, because bops is a word, right? BOPS is a word. Anyone want to give me another one? I believe bopped is a word. So if you remove the initial bop, it would be this, right? Because bopped with 2 P's is a word. So when I went through my list of English words, and this is what I found. We also get purr, because bopper is a word in my list. We also get, anyone think of another one? Ping, and, oh, of course, purrs, right? And one more important, those are kind of silly, but this is also kind of silly, but important. The empty string, all right? The empty string is in there because bop itself is already an English word. If I take that and remove the original or the initial bop from it, so this empty string is there. This is since bop. It's already a word in E. So if I start with that one and take away the BOP at the beginning, I end up with the empty string. All right, this is the derivative. I just got a text from Juliana. She must be home early. Oh no, the school ends at 1 for them, so her name appears as Juliana the Queen, not this Juliana. Juliana the Queen.
I am a queen.
Yeah, maybe you are also Juliana the Queen. You guys, I'll let you guys decide. Discuss amongst yourselves. All right, so what is the connection? This is not just sort of cute little playing around with words. What's the connection between this and regular languages? Well, if you recall, all right, I'm gonna unsubscribe from this chat here. Turn off. Okay, I think I did it.
Why are you so excited about that?
5th graders, you know what I'm saying? What are you going to do? Okay, what does this have to do with anything? Remember, these derivatives, I mentioned this last time, derivatives correspond to moving the start state in a DFA. Very specifically, if my language was L, if we start with L as my language, say L of M, and move the starting state through one of the arrows, say an arrow with an A on it, the language changes and it becomes DA of L. That's because in the original machine, if I move the starting state through a L, that means through a A, that means rather than going across the A first, you don't have to go through that A anymore because you start yourself off closer to the accepting state. And so you can remove the A's that used to be there in the original language, all right? This is what the derivatives have to do with DFAs at all, although this, as we'll see, is very, the idea can lead us to a method for determining if something is a regular language or not. Check it out. Here is, well, this is the same example that I had from last time, but I want to give some names to these states this time. This was, I'm going to call this, sorry, I meant to call this one R, Y. It was like this. And then I had this failure state over here, which I'll call X. And then A is going down here. All right, this was an example that we discussed last time. If we move, so as written, the starting state is S, but here, if we move the starting state to T, then the language becomes derivative with respect to A of L, right? M is the original machine, but if I were to change the machine by moving the start state, the language of that new machine would be the derivative with respect to A of the original language. What if I move the starting state to X? moving to x makes it ddb of the original language, which in this particular example is the empty set. There are no accepted strings starting from x. And that's because in this example, all of the accepted strings begin with a. And so if you take the derivative with respect to b, there are no strings that begin with b, and so you get nothing for the derivative. What about if I move this to, I'm going to try and continue up here so you can still see everything. Moving the starting state to R makes the language, well, moving it to R from here is where it starts. To get to R, you go through A and then B. Actually, this makes the language this. The derivative of A, B. And in fact, it is a true fact about the derivative that the derivative of AB is the same as the derivative of A of the derivative of B of the original language, if you want to think it that way, all right? Because you do AB to get to R from the original starting state. This means there's some other interesting things you can say. For example, moving the starting state to X makes it D by dB of LM. But this here, I gotta keep that picture on screen. This is also, you could think of it as D DAA of L. Because one way to move to X from this starting state is to just go down here across the B. But you can also move to X by going to A and then this A, right? And if you believe everything that I said here, it must mean that these two derivatives are equal, all right? And if you think it through in this particular example, actually you will see both of those derivatives are equal. They are both the empty set. Because this one is the empty set because none of the accepted strings begin with B. This one is the empty set because none of the accepted strings begin with AA, all right? But in any case, by looking at the diagram, just by looking at the diagram, we can see here that this is what I just said before. The derivative with respect to B is the same as derivative with respect to AA of L. We know that because on the diagram, doing a B arrives at the same point as doing an A followed by A. And there are many other equalities that you can get from the diagram. For example, derivative with respect to A of L is the same as, can anyone give me another derivative which is the same in this example? So A moves you to T. Can you give me another string whose derivative will be the same? Yeah, A, B, B, B. All right, A, B cubed. All right. These must be the same derivative because doing A ends you up the same place as doing A followed by B cubed, right? They both end you up at T. And so those derivatives must be the same. In fact, there are only 5 states in this diagram, right? So if you think about it, there's only 5 different places that you could possibly move the starting state to. And each of those places would have their own set for the derivative, but there's only 5 of them. So there are only, in this example, there are only 5 possible starting states. So that means that any derivative with respect to whatever, any derivative you take must be one of these just 5 choices, right? There's the one that you get, if you just start at S, which is no derivative at all. There's the one that you get here, which is the A derivative, but it's also equal to many other derivatives. There's the one you get here, which is the B derivative, but it's also equal to many others, right? And how many others are there? There's only 5 possible ones. So any derivative of L must be one of 5 different sets, or 5 different languages, if you like. You can take the derivative with respect to any string you want. There's only 5 possible different answers that you could get from those derivatives. There will be many, many, many different sort of coincidental things that end up giving you the same answer, because there's only 5 possible correct answers for the derivatives here. This actually is not at all obvious, but I think by the time we're here in this conversation, I hope you will agree with me. This is a basic property of DFAs. So any DFA language, any regular language really, because there's only finitely many states in the DFAs, there's only finitely many possible answers you could get from the derivative. Any regular language has finitely many derivatives. This is a basic fact of regular languages, because a regular language, you can write a DFA for it. The DFA has only finitely many states, and so most of the derivatives are always just going to give you the same answers. There's only finitely many different possible answers you could get when taking the derivatives. And this is the big theorem about regular languages and derivatives. Maybe I'll write the theorem. I'm going to write the contrapositive of this because it's the format in which we use it more often. Remember the contrapositive of a logical, if you have, say, P implies Q, the contrapositive is not Q implies not P. That means the opposite. So this one, if I wanted to state it as an implication, I would say if L is regular language, then L has only finitely many different derivatives. The other way around would say if L has infinitely many different derivatives, then L is not a regular language. All right? And this turns out to be fairly easy to check. Remember, my goal for this whole little bit that we're talking about is a general purpose method which you can use to show that something is not regular. Because to show it is regular, you just make a regular expression for it, or an NFA or something. To show it's not regular, quite a bit more difficult, but this actually is not so hard, a way to do it. This is how you can show that a language is not regular. So let's do first of all, our favorite example, which is kind of an easy example, is this language, A to the n, B to the n. This is everybody's favorite example of a non-regular language. All right, I'm going to do like a little proof, I suppose, although there's not so much to this. What we have to demonstrate is that there are infinitely many possible different answers you could get when taking the derivative with respect to various other strings. So maybe I'll just say that first. We'll show there are infinitely many different derivatives. This is always how we're going to show that a language is not regular. And you do have to be a little creative sometimes about this. You have to think up for yourself some way of writing down infinitely many different derivatives. You sort of have to pull this out of nowhere, but I think you'll see fairly soon that this is usually pretty easy to decide how you're going to do this. I have to somehow demonstrate infinitely many possible derivatives. Check it out. I'm going to start with d by dA. I'll call this L, right? Can you write down in words what this is, or using the set builder notation? This would mean you take anything from L, but you take away the A at the beginning. So this would look like A to the n minus 1, followed by B to the n, right? And this set here is different from the original L, right? The original L has the same number of A's and B's. This one has one fewer A, right, than the amount of B's. What about dA squared of L? Can anybody say what that is? Yeah. Yeah, right. A to the n minus 2 bn, where n is any number again. Right? This is a set in which you have removed two a's from the beginning. And, I hope you agree with me, this set is also different from the other two sets there, right? This is different from L itself, and it's different from DDA of L, right? All three of these sets that I've written on the screen there are all different from each other. Can you see how I could make infinitely many different derivatives? The answer is you just keep on doing this, right? I did a and then a squared, but you could do a cubed and a to the 4. You get a different thing every time. So the way that I'm going to write this is I'm going to say let di be derivative with respect to a to the I of L. I'm trying to write a whole list of like infinitely many different ways that you could do this. And if you write this in terms of like what it looks like as a set, n minus I, a to the n minus I followed by b to the n. And there are infinitely many different possible I values here. So what I'm describing here is infinitely many different sets. Now, are they actually all different? That's what we have to demonstrate, that these derivatives are really all different. Well, they are all different, and we could describe, say, in words. So what di is, all things like a star, b star, maybe. It's a bunch of a's followed by a bunch of b's, where the number of a's is I less than the number of b's, right? Is it confusing when I write it that way? I don't think there's a better way to say it, but the number of a's is I less than the number of b's, all right? Thus, each di is different, right? It's not like somehow d2 is the same as d4 or whatever. No, they're all different because for each different value of I, I'm describing a different set here. And so L has infinitely many derivatives. So L is not regular. All right, this is how we do it. Any questions about all that I just said there? So there is some amount of technique to this, or some kind of intuition. You have to get yourself to a point where you can look at this example, and I immediately knew that I was supposed to take the derivative with respect to a over and over again. That's because what I see on these strings, they all have a bunch of a's stacked up at the beginning. So it's reasonable for me to think of taking the derivative with respect to powers of a. This is something that I suppose takes some practice to be able to look at the language and decide for yourself what kinds of derivatives to use. But really, it's not. I mean, it's typically not going to be difficult. Let's try another example. How about on the alphabet A, B, C? That's A, B, C. Pick a C there. Let's show that this language, A to the n, B to the n, C to the n. This also is not regular. All right. Actually, let's make it slightly more interesting. This one, the proof is almost like exactly the same as what I just wrote. So maybe I'll just for fun, let's write B to the n, A to the n, C to the n. I put it in a slightly different order, all right? Okay, let's do it. So I'm going to write this as a proof here. But really, there's not much to say. Your proof for all of these will begin by just telling me what all the derivatives are going to be. Then you have to somehow explain why all those derivatives are different from one another. Anyone want to suggest? What should I be taking the derivative of this time? B. Yes. Now you have to do sort of a whole a whole bunch of them, d sub I, I'm going to do derivative with respect to b to the I, right? So the first one is just b, the second one is b squared, the next one is b cubed, etc. And can we say what this looks like as a set? Anyone want to say? You can kind of write this same sort of format here, but yeah, b to the n minus I, a to the n, c to the n, right? And are these really all different from one another? They are, because, say, when I is 1, it means there's 1 less b than the others. When I is 2, there's 2 less b's. Those are all different from each other. So you just have to say something like that. So I will, usually the way I'm going to explain this is just by, I will try to say sort of in words what di is. Di has, maybe I'll just say same number of a's and c's, but I fewer b's, right? That's what di represents. And these are all going to be different. Depending on each different I gives you a different set here. D1 will have 1 fewer. D2 will have 2 fewer. Those are different. So these are all different. So L has infinitely many derivatives, and so it is not a regular language. All right. That's how we do it. Not a regular language. You're going to see a theme, as we do this. I hope that you will begin to kind of develop some sort of intuition about what sorts of things are regular and what sorts of things are not regular. One classic kind of attribute of a non-regular language is one in which you have specific, repeated, like same number of something or other. This one is all about the same number of A's and B's and C's. That is something that, generally speaking, cannot be done with a regular language. Regular language can decide something like evens versus odds, or something is a multiple of 7 or whatever, but two separate things in the string having the same length or the same number of things or something like that is generally not possible for a regular language. All right, let's try another one. This one is slightly different, and then we're going to do some that really look quite different. But let's try, here's another slight variation. BA to the n followed by AB to the n. So this has some number of BAs followed by the same number of ABs. All right. This is not regular. Let's try and do my proof here. I'm just going to straight out the box, off the dome, say what DI is. You want to be taking certain derivatives repeatedly. Usually your derivative will look something like this, right? Derivative of something to the I. In the previous examples we did, it was just A to the I or B to the I. Any ideas for this one? BA to the I, yeah. So BA to the 1 will remove that first BA, then BA to the 2 will remove 2 of them, and so on. Yeah, it's not so hard to look at the format of your set and decide what derivatives you're supposed to be taking to show that it's not regular. Okay, now, so this, if I were to write it as a set, what does it look like? It looks like BA to the n minus I followed by AB to the n, right? So what we see here is some number of ABs at the end, and at the beginning, I fewer BAs, right? This is a little hard to say in words, but so DI has strings. I'll try and say this as best I can. Like, maybe it's easier to use sort of a regular expression type. it's some amount of BAs followed by some amount of ABs, where specifically the number of BAs is I less than the number of ABs. All right? And since that I is going to be different every time, these sets will be different every time from one another. So I say, as we always do, sort of to conclude here, these are all different. So L is not regular, right? L has infinitely many different derivatives, so it's not a regular language. All right, this is how we use the derivatives to show that something is not a regular language. I thought it might be interesting to see what would happen if the language actually was regular. Where would this argument break down? Because sometimes when you do these proofs over and over again, you know, on the homework I'm going to ask you to do a bunch of examples like this. You'll begin to feel like you're just writing the same proof every time, and maybe you will wonder to yourself, couldn't I really just write the same proof every time? Like, does anything matter here, or can I just say exactly the same thing every time? No, something does matter. So I thought we should do an example where this doesn't actually work. How about a to the n, b to the m? So here I have some number of a's followed by some other number of b's, but they don't have to be the same number anymore. This actually is regular. Can anyone give me a regular expression for that? Some bunch of a's followed by some bunch of b's. Yeah, this is not a tricky one, really. If you remember your regular expressions, this is just a star b star. So if we try to do that derivative style proof, something has got to go wrong. All right, let's try the same derivatives argument and see where does it break down. I would say let di, I mean, looking at the format of these strings, I would do derivative with respect to ai of L, right? If I didn't know any better, this is how I would choose my derivatives. And then to write this out, I would say a to the n minus I, b to the m, right? That's what it looks like. Next in the proof, I would try to describe this set in words and then explain why it is that these sets are all different from one another. But actually, in this case, di is everything like a star, b star. You know, ordinarily I would say where there's I less of the a's than there are of the b's. But actually, in this case, the number of a's doesn't have anything to do with the number of b's, right? The number of b's is m, and the number of a's is n minus I, but that could still be anything with regard to m. So di is everything like a star, b star. Actually, there's nothing more to say here. Like, there is no further restriction on what the number of a's has to be less than the number of b's. No, it still could be anything. All right. So actually, in this case, all of the di's are the same, right? Even though, I mean, when you write this formula, it looks like they're different because if you change the I, it looks different in that formula. But if you think it through, you realize you're going to get the same set no matter if you use I equals 1 or I equals 2 or anything. They're all the same set. They're all, actually they're all the same as L, right? All the di's are the same. Actually the same as L, right? And so, in fact, we have not demonstrated that there are infinitely many different derivatives. What I wrote down looks like it might be infinitely many, but actually they're not. They're all the same. So these are not infinitely many derivatives and infinitely many different derivatives. All right, so we have not shown that L is not a regular language. In fact, we already know L is a regular language. But I just wanted to try and demonstrate where this whole thing can break down. You can't just write the same proof without thinking about it all, because it doesn't always work. Sometimes it don't work. Any thoughts about that? Questions? Great. All right, let's try one example that's a little more interesting, a little more complicated perhaps. How about this? This is another non-regular language, but it does not have to do with repeated n's in the exponents, which all our previous examples have. The set of all strings that looks like this. X, XR, where X is in AB star. And I'll tell you what this R, X to the R means the reverse of X, which means exactly what you think it is. It's just you read the string backwards. All right. So, for example, in this L, so L includes things like AAB, BAA. That's because you can break this down into a X followed by a X reverse, right? So that is part of L, or something like, I don't know, BABAB, ABAB. Is that right? No, I need another B in the middle. All right, now this is part of L. This is almost the same as saying that it's like the palindrome strings, but it's not quite that, because there has to be even length in order for them to be in this set. All right, those things are in L. This, it turns out, is not a regular language. L is not regular. How can we demonstrate that? Using the derivatives. I'll just write this again here. X followed by X reverse. X is in AB star. I got to take some derivatives, as usual. The problem is when you look at the format of the strings here, there's no clue about what we should do the derivatives, because we don't know, for example, we don't know what letters these strings begin with, right? It turns out it doesn't really matter. So I'm going to do my favorite old thing here, which is this. Now, why did I choose A rather than B? It doesn't matter. Actually, you can do it with B also, if you want. I'm going to take derivatives with respect to A over and over again. You got to think a little bit about this, and this is slightly tricky. Can we say what this looks like as a set? Now, remember what this derivative means? It means we are removing A to the I from the beginning of strings in the original language, all right? Now, for this language, we don't even know if they started with A to the I at all right? In fact, many of them do not start with A to the I, but at least some of them do, and we only consider the ones which do start with A to the I, and from those, we remove A to the I from the beginning, all right? So this set, I don't think I'm ready for this equal sign yet, but I'm just going to say we consider any string in L which begins with A to the I, and then remove that A to the I from it, right? And what about all the other strings which don't begin with A to the I? Well, we just don't care about them at all, right? We only consider the ones which do begin with A to the I, and from those, we remove A to the I from the beginning of them, all right? And then we consider what remains, what's left over in such strings after we remove A to the I from them. Well, it might be helpful to say, what do those strings look like to begin with? If they begin with AI, so if a string in L begins with AI, A to the I mean, then it must look like, if it starts with AI, then it has some other stuff after it. Maybe I'll call it Y. I don't want to call it X just because I already used X up top in the definition of L. Let's say it starts with A to the I and then has some other stuff. What does the rest of it have to look like? Well, it must be, since it's part of L, this string must have this format. Something followed by the reverse of that same something. And so, it must look like this. How do you like that? It has to start with something, which I've already said it's going to include A to the power I, then have some other stuff there. But then in order to be an L, the rest of it must continue to look like, first of all, the reverse of Y, followed by another A to the I at the end, right? Basically, if it starts with A to the I in this language, it has to also end with A to the I. And it can have some stuff in the middle, all right? And so that means DI contains strings like Y, Y to the R, A to the I. I just wrote what I wrote before, but I removed the A to the I from the beginning, right? This is what the elements of DI look like, the derivative. All right? So these strings, in particular, end in A to the I, right? They have A to the I at the end of them. And here is where you can see that these will all be different for different i's, right? So for I equals 1, all these strings have an A at the end. For I equals 2, all these strings have 2 A's at the end. For I equals 3, they all have 3 A's at the end. These sets cannot be the same. Maybe some will be subsets of each other, but they're not all the same set, right? And so, DI are not all the same set. In fact, they are all different from one another. That's more. It's not good enough that they're not all the same. I have to say, DI are all different. Right? D1 contains only things which end with one A. D2 contains things which end with 2 A's, and so on. Those are all different sets. So that means that L is not regular. It has infinitely many different derivatives. All right, that's a tricky one. Any questions about that one? That one is a little harder. Okay, I had some for you to try, but we don't have enough time for that, I don't think. So maybe I'm going to do one more example. This one is very similar to the one to this one that I just did. So this was x followed by x reverse. Let's try a similar one. This is just x followed by x. X is an AB star, all right? So this is any string which consists of one thing followed by the same thing again, all right? Actually, you could, if you want to be cute about it, you could just write x squared, right? This is the set of all squares, strings which are squares, where square means something like abba, right? It's the same thing twice, right? That's what these this L is, all right? We can do a similar, very similar thing with the derivatives as we did in the previous example. So I'm going to consider, so I'll just write out, this is not regular. And my proof of this involves doing derivatives. And I'm going to do dA every time. Big DI equal dA to the I of L. This is going to go very much like the previous example did. Actually, maybe a little easier. I don't know. Remember the way we did this in the previous example. We said something like, if one of those strings does begin with A to the I, then that whole string must look like this. In our example here, we can just modify that slightly. So if we begin with, if the string begins with a to the I, then it looks like, anyone want to tell me the modification from before? This is what, in this language, because it was x followed by x reverse, it would have to look like that. What about in this case? Folks back home, you can chime in if you like. I hope I'll hear you. My sound is off. What do you think?
AIY, AIY.
Yeah, AIY followed immediately by AIY. If the string is in this set, then it has to look like AI with some other stuff, followed by AI with some other stuff. Okay, and then, so then DI is, or it contains strings like y, a to the I, y. Yay, with I, a's in the middle, right? And those sets, DI, will all be different because D1 is the one with one A in the middle. D2 is the one with two A's in the middle, and so on. Those are all different. So each DI is different. So L has infinitely many derivatives, and so it is not a regular language. So L is non-regular. It's true. All right. This is how we use the derivative to show something is not a regular language. And I think that'll do it. We got a few more minutes left, but I wanted you guys to try some. So we will start off next time with some more examples. All right, thank you for coming today. I don't know why you folks didn't come. We had a great time here without you. See you all on Friday. No homework today, no quiz on Friday. Bye. Mm.